So in this one we're going to go over just a couple of useful properties of the Dirac delta function. So properties of Dirac delta. So let's just remind ourselves of the, I guess you could call it, the fundamental property, which is just the idea that f of x naught is obtained by performing this integral over the delta function. You can think of this as the defining property of the Dirac delta function. And so what's happening is, upon evaluating this integral, we effectively just pluck out the value of the function f of x at x naught, which is dictated by the Dirac delta. The simple specified version of this case, when x naught 0, is just this result here. And it's this specialized case that we'll focus on right now, because it's sufficient to explain a couple of the properties of the Dirac delta. Okay, so the first one is just a very simple one, symmetry property, which just says that delta of minus x equals delta of x. Okay, so that's useful. And it should be relatively clear if you remind yourself how we got here. So we started with this kind of rectangular step function that is symmetric about x goes to minus x, height 1 over epsilon, and then we considered the limit of shrinking epsilon, which causes the width to decrease while simultaneously the height increasing. So you can imagine this kind of limiting process in which at every step in the process the area under the curve is conserved. And essentially, because we started off with a symmetric function, there's no reason why in the limiting procedure we would violate that symmetry. So this is true, and it also holds for some of the other distributions I showed you that you can use to build the Dirac delta function. So like something like e to the minus absolute value of x over epsilon, and I think there was a factor of 1 over epsilon, something like that. This one's also symmetric, so this property holds. Okay, the second property is a little more interesting, and it says that delta of cx is 1 over c delta of x. Okay, so here c is some constant. We'll take it to be real. We will also take it to be positive for sake of argument. So what do we really mean by this is, well, when we're talking about delta functions, we're pretty much always working underneath an integral sign. So the question is essentially, if we run into something like this, how do we proceed? And the idea is just perform a simple change of variables. So we'll let x go to x prime, which is cx. And then we can invert that to get x is x prime over c. Similarly, we get dx prime is cx, or c dx, or equivalently dx is dx prime by c. So substituting those in, we have to consider how the bounds of the integral change. This is why I'm choosing to focus on c positive. If I send x to positive infinity, as long as c is also positive, then x prime will also go to infinity. assuming C is finite. So the bounds don't change, because similarly if I send x to minus infinity, x prime goes to minus infinity. You can do a similar argument with negative c, and that's how we arrive at this general form here with the absolute value. But for simplicity, we'll just focus on the c positive case and to show the general way in which this kind of pattern emerges. So continuing now, so we're changing variables. So we now change the bounds. This becomes delta cx goes to x prime, and f of x goes to f of x prime by c. And then dx becomes dx prime over c. So we already are seeing where this factor of 1 over c emerges. And if I just pull it outside of the integral, we can go right ahead and evaluate this, because it's of the exact same form as this relation here. It's just that now our function f of x has a slightly different argument. But it's still true that this delta function will pluck out the value of f evaluated at x prime equals 0. Okay, so this thing just gives us 1 over c times f of 0 over c, which is 1 over c f of 0. Okay, so that's cool. If we replace f of 0 in this expression by this formula here, that is, we say this integral, which we've just evaluated, is 1 over c f of 0, which is nothing but 1 over c times this integral here, f of 0, delta of x f of x dx, I can bring the factor of 1 over c back inside, put it underneath the delta sign, or the delta function, and if we just compare the left hand and the right hand side, we see that these two representations of the delta function have to be equivalent. So we conclude that delta of cx equals 1 over c delta of x. Okay? So almost as promised, but in the special case where c is positive. One thing I would like to mention is something about the dimensions or the units of the delta function. So let's see. If we just go back again to the fundamental, or we can even consider the more general case here, fundamental relation for the delta function, f of x naught is this thing here. Okay. We have some function f, it has some units, maybe it's temperature, maybe it's pressure. Whatever the units of f happen to be, upon doing this integral we pick up an extra factor of dx here. So this has dimensions of length. So in order for the units on the left hand side to be consistent with the units on the right hand side, which already carries a factor of f, this delta function better have units of the inverse of dx, which in this case is inverse length. So we might say that delta of x, the dimensions of delta of x, have the same dimensions as the inverse of x, the inverse dimensions of x, I should say. And then from property 2 here, this makes a lot more sense, because if I just move the c to the other side, I'm going to rewrite this. So I have delta of cx equals, move the c over, delta of x. Then the dimensions have to be consistent, so maybe I don't want to move it over. 1 over c delta of x. Whatever the dimensions on the left have to be equivalent to the dimensions on the right. So the dimensions of delta of cx are equal to dimensions of 1 over c times the dimensions of delta of x. So we already just showed that the dimensions of delta of x have to be the inverse dimensions of x. So this is dimensions 1 over c, dimensions of 1 over x, which is 1 over cx. And so indeed, the dimensions of the argument, the dimensions of the delta function with argument cx have dimensions of inverse cx, the inverse dimensions of the argument. So that's another important thing to remember. Okay.